In this video, we'll talk about the calculations that allow us to objectively compare the means from each of the different factor levels to one another. After we talk about these calculations, we'll show an example and then dive a little bit into the theory as to why this works out statistically. So first of all, in the previous examples we've been talking about, I've kind of used the idea of a TV signal where you've got the show you're trying to watch and white noise or static. And I've kind of talked about the sum of squares for the treatment as the TV show signal, and the sum of squares error is kind of the white noise. And though this is a good kind of comparison as to maybe a big picture view of what we're looking at, we actually can't directly compare the sum of squares treatment to the sum of squares error. However, there is a quantity called mean squares which can be compared. And the mean squares is really just the sum of squares divided by its degrees of freedom. So if you remember back to the t-tests had differing degrees of freedom depending on the test. So like a one samples t-test had n-1 degrees of freedom. A two samples t-test had n-1 for each group, or in 1 plus n2 minus 2 degrees of freedom. Now we have that for our different components of the analysis as well. So we have the total, and similar to the sums of squares, the degrees of freedom total is the degrees of freedom for the treatment plus the degrees of freedom for the error. So the total degrees of freedom is capital N minus 1, or A times N minus 1, or again I times J minus 1, depending on the notation. And that can be broken down into the two pieces. The degrees of freedom for the treatment, which is A minus 1. If you think about this, this is the number of groups minus 1. So treatment is looking at the movement of the group means. So the number of degrees of freedom we have is the number of group means minus 1. Now this one's a little bit more complicated, the degrees of freedom for the error, but remember that error is the movement of data within the group. So we have A groups, so we're going to have for each of these A groups the number of replications minus 1 within the group. So we have within the first group n minus 1, within the second group n minus 1, within the third group n minus 1, and then we add all those up, and that gives us A times n minus 1, which is the degrees of freedom for the error. And so how do we calculate the mean squares? Well, we take the sum of squares that we had and we just divide it by the degrees of freedom. So the sum of squares treatment divided by the degrees of freedom for the treatment is the mean squares, the mean square for the treatment. The mean square for the error is the sum of squares error divided by the degrees of freedom for the error, and that's what gives us the mean squared error. Now, if the treatment means are equal, then the treatment and error means will theoretically also be equal. And if the treatment means differ, then the treatment mean square will be larger than the error of the means than the error mean square. So actually, we'll talk about this a little bit more later on. But this idea that the mean squares are going to be the same as long as the treatment means are equal, so that's under the null hypothesis. The null hypothesis is that the treatment means are equal. So under the null hypothesis, these values are going to be the same. And then if the null hypothesis isn't true, that is, the treatment means are all different from one another, then this mean squared treatment is going to be larger than the mean squared error. So you can think about there's the kind of neutral is that there's as much white noise and TV show signal as each other. So I can't really distinguish between white noise and TV signal because they're both the same strength. So it's just all going to come in as psh, and I can't really tell the difference. But as the TV signal gets stronger and stronger and stronger, then my TV show starts to come in and it starts to overwhelm the white noise such that the TV show that I want to watch is what I end up seeing. All right, so the analysis of variance is almost always summarized in a table, and this table is called the ANOVA table. So this is a very, very common thing that you'll see, and a very, very, very important thing that you'll see. So the ANOVA table is always broken down like this. Sometimes you'll see another column over here for a p-value, or sometimes an expected value column. We'll talk about those later. But you always have source, sum of squares, degrees of freedom, mean squares, and F. And you'll see a couple of dashes because we don't calculate mean squares and F for everything. We just calculate mean squares for the treatment and error, and we just calculate F for the treatment. These sums of squares are the same thing that you've seen before. The sum of squares treatment is the difference between the group and the grand mean. The sum of squares error is the difference between the data value and the group mean. And the sum of squares total is the difference between the data value and the grand mean. So this is the traditional breakdown that we've had. And again, they're summed over all the groups and all the observations within the groups. The degrees of freedom are what we just saw earlier, and then the mean squares are what we just saw earlier. The sum of squares divided by the degrees of freedom for each of the individual components. So we'll discuss computing this in R, and this isn't necessarily trivial to compute, yet you sometimes have to use a few tricks to get to this. It's not necessarily straightforward to do. Now, all of this work is to calculate an F statistic. All of this is to calculate like the T statistic that we had in our t-test. This F statistic is the thing that we're actually going to end up testing. So all of this work, all of this calculation is to end up with our test statistic F. And this test statistic F is going to be compared to an F distribution. Now, F distributions actually have two sets of degrees of freedom. They have the numerator degrees of freedom for the treatment and the denominator degrees of freedom for the error. So our numerator degrees of freedom is A minus 1. Our denominator degrees of freedom is A times the quantity N minus 1. And so for our F statistic, we have F, A minus 1, and A times N minus 1. And of course, we reject the null hypothesis if F is greater than a particular value. So typically we'll have 1 minus alpha instead of alpha. Sometimes, typically this should actually be 1 minus alpha. I apologize about that. But F sub 1 minus alpha, comma A minus 1, comma A N minus 1. So our tail that we look at is the upper tail test on the F statistic, and we'll talk about why that is later on. Now, one thing to notice on here is actually because of the fundamental ANOVA identity. What is the fundamental ANOVA identity represented on this table? Well, the fundamental ANOVA identity is that this total sum of squares is the treatment sum of squares plus the error sum of squares. So if I put a little plus sign in the middle here and a little equal sign here, this one plus that one should equal the bottom one. So this is the fundamental ANOVA identity. But what's interesting is that that means if I have two of these, I can calculate the third one. So if I have the treatment sum of squares and the error sum of squares, I don't have to do a calculation for this third one. I could just add these two together and get the third one. Of these three, the one that tends to be the hardest to calculate is the error sums of squares, because the total sum of squares is just the numerator for a regular variance. The treatment sum of squares only involves the A factor levels, and I don't have to worry about, recall that we could just do N times the A factor level, so I don't have to worry about replications. It's the error where I have to worry about both groups and replication, so it involves the most calculation. So often what we'll do is we'll just calculate the total sums of squares, the treatment sum of squares, and then take the total sum of squares minus the treatment sum of squares to get the error sum of squares. And again, that comes from that fundamental ANOVA identity where this top one plus the middle one's the bottom one. And just by subtracting the top one from both sides of that equation, the bottom one minus the top one gives you the middle one. All right, so I say the real by hand because the textbook presents a few shortcuts if you were doing this by hand. But recall in our class we tend to do quote unquote by hand in R, and that's not really by hand. These are useful if you're doing by hand. And what I mean by that is, let's say that you actually had to do this like with a paper and pencil. That sounds pretty terrifying, right? But if you were doing that, these calculations are really nice, and you'll note that instead of calculating the sum of squares error, what they end up doing is they find the sum of squares total and the sum of squares treatment and then subtract them so that they don't have to do the more lengthy calculation. So I'm showing this, again, we aren't going to have to use this really in our class because we never have to do it on paper without a calculator kind of a thing. And in R, when we do it quote unquote by hand, this isn't necessarily the easiest way to go either, though we could do this, and actually maybe it'd be useful to try this out when we get into R. I guess we'll see. But the other reason I show these is because our example where we see our ANOVA table from example 3.1 does use them. So in our textbook example, we have the data from what we were looking at. So we were looking, recall, at the etch rate given these different powers. So we found the sum of squares total, we found the sum of squares treatment, and then we subtracted them to get the sum of squares of the error. And recall that this, again, we talked about these different components, and we know sum of squares total equals sum of squares treatment plus sum of squares error. By the way, this isn't true with mean squares. Mean squares total doesn't necessarily equal mean squares treatment plus mean squared error. But the sum of squares total equals sum of squares treatment plus sum of squares error. That works. But we can't compare sum of squares treatment and sum of squares error. However, we can use this and the information about the degrees of freedom to construct the ANOVA table. So actually, before I actually show the printed out ANOVA table, let's try to think through what the different components are going to be. I've got the treatment, the error, and the total. So that's my source. My second column, I had the sums of squares. So the sum of squares treatment is going to be this 66,000 number. The sum of squares error is going to be this 5,000 number. And then the sum of squares total is going to be that 72,000 number. I've got the degrees of freedom. So degrees of freedom, A minus 1. Number of factor levels minus 1 is the degrees of freedom for the treatment group. So I had four different, I had 160 watts, 180 watts, 200 watts, and 220 watts. So I had four different factor levels. So A is 4. 4 minus 1 means that my degrees of freedom for the treatment is going to be 3. Working through the second one, again, mentally, or feel free to write this out in your notes. I'm going to display the answers in a second here. But the second one, A times N minus 1. Well, A is 4, we just talked about. N, what is N? Number of replications within a single factor, lowercase n. So within a single factor level, I had 5 replications, and A is 4, so I end up with 4 times the quantity 5 minus 1, or 4 times 4. So my degrees of freedom for the error is 16. And then my total degrees of freedom, you can just sum these two degrees of freedom. So I've got 3 plus 16. Total degrees of freedom is 19. And again, that's capital N minus 1. So if I had 20 total wafers in my study, or 20 total coupons, then 20 minus 1 is going to give me 19 as my total degrees of freedom. And then, of course, I do the sum of squares treatment divided by degrees of freedom treatment to get the mean squared treatment, and sum of squares error divided by the degrees of freedom error to get the mean squared error, and then I would calculate the mean squared error, or mean squared treatment divided by mean squared error to get F. So doing all this, again, we did all this kind of in our heads before. 3, 16, 19, the sum of squares look right, the different sources of variation look right. I'll note that they list the variable name instead of quote-unquote treatment, and that's just fine. That's actually relatively common to do. And then they divide. 66,000 divided by 3 gives me roughly 22,000. Yeah, so that looks right. They take 5,000 divided by 16, get this 333 number. So they just literally took whatever was in the sums of squares divided by degrees of freedom to get the mean squared. Note that they don't do this for the total. That's not something we do for the total. The purpose is to get to F. And all we need to do for F, all we need to get there, is the mean squared treatment and the mean squared error. So after I have these, I literally take this top number divided by the bottom number, and that's what gives me F, and that's what all this work was for. So this F statistic is like my test statistic. It's like my T statistic in a t-test. Comparing to a F distribution, I find the p-value is very, very small, and so I would declare this to be a statistically significant relationship. So what does that mean? That means that there is evidence that at least one of the means is different from the other. So there is enough evidence here to declare that the etch rate for one of the power settings is different than for one of the other power settings. I don't know which one. Maybe all of them are different. Maybe only one is different from the other 3. I don't know. I don't know if it's bigger. I don't know if it's smaller. That doesn't tell me that here. All I know is that it's different. So this is the benefit of ANOVA, is it tests 4 factor levels all at the same time in a single p-value. Is pretty cool. The problem is well, I don't know what the difference is, and so we need some more analysis to follow that up. All right. So why does this work? What's a bit of the background here? And this is something that isn't necessarily always talked about, but what is the theoretical backing here? And this will connect a bit to your mathematical statistics background. So first of all, it's important to realize that we're assuming that we're sampling from normal populations, and that our error is normal. So the sum of squares treatment and the sum of squares error, we're assuming that these are components from a normal population. Now, if that's the case, then if we take these sums of squares and divide it by the population error variance, and we don't ever know this number, this is for all the data, like in the whole world. So we don't know this number, but if we did know this number, if we took the sum of squares and divided by that number, that would be distributed as a chi-squared, with the same degrees of freedom for the chi-squared as is degrees of freedom for the sum of squares. And this is true for sum of squares treatment and error. You'll note that the chi-squared has different degrees of freedom because the sum of squares treatment has different degrees of freedom than the sum of squares error. Now the cool part is that if I have two chi-squareds and divide one by the other, then the ratio of two chi-squareds over the degrees of freedom is an F distribution. So recall that from math stats. Now what's cool here is that Cochran's theorem says that these are two independent chi-squared random variables. So because these are independent, I can take this particular ratio as an F statistic. So what I end up doing is I take this chi-squared and I divide it by its degrees of freedom, and the second chi-squared and divide it by its degrees of freedom. Now what you don't see here is that when I take the chi-squared and divide it by the degrees of freedom, that I'm kind of canceling out the sigma squared. So if I have a divided by sigma squared on top and a divided by sigma squared on bottom, then those two divided by sigma squareds cancel, and all I'm left with is the sum of squares treatment divided by the degrees of freedom over the sum of squares error divided by the degrees of freedom. And if you think about what the sum of squares treatment divided by its degrees of freedom is, this is the mean squares treatment. Sum of squares error divided by its degrees of freedom is the mean squared error. So the F ratio is just the mean squared treatment divided by the mean squared error. It's pretty cool. So another component here is the expected value of each of these, and we'll get into these more when we talk about random effects ANOVA. The expected value of the mean squared treatment is the population error, so the population error value, plus the sum of squares, in essence, of the, actually this should be from I equals 1 to A, not 1 to N, so I apologize about that. But it's the sum of squares of the factor effects. So in this particular case, this is our expected value of the mean squares treatment. The expected value of the mean squared error is sigma squared. Now, we won't go into this. Actually, we will go into this later on. But for right now, just take this as a definition. What I want you to look at for these two things, though, is that recall that for the F statistic, we have mean squared treatment divided by mean squared error. So we have this mean squared treatment term divided by the mean squared error term. And if you think about that, well, both of them have a sigma squared, and the only difference between them is this kind of second component on the mean squared treatment, the expected value of the mean squared treatment. And the second component is just made up of the factor effects. So if there are 0 factor effects, all the means are the same, then this just is all 0, and the mean squared treatment is the mean squared error. The expected value of the mean squared treatment is the same as the expected value of the mean squared error. So actually, nothing going on in an F statistic isn't 0. So the statistic when nothing's going on in an F statistic isn't like the T statistic where it's 0 if nothing's going on. If nothing's going on in an F statistic, we get mean squared treatment sigma squared divided by mean squared error sigma squared. So if nothing's going on in F, the default value is 1, not 0, because we're doing a division problem. Now, if something is going on, what happens? Well, the treatments get some numbers, so they're different than the grand mean, so these get numbers, and they get squared and added up, and we don't really have to know what's going on here. What we do need to understand is that the treatment, whether it's positive or negative, the treatment effect is going to be squared. So this second term is going to be positive, always. So what does that mean? Well, what that means is that on average, if something's going on, then mean squared treatment divided by mean squared error, the expected value is going to be a number bigger than 1. We have something bigger on the top divided by something smaller. That means it's going to be a bigger ratio than 1. So this is why we do only an upper tail test, not a lower tail test, is that when we have treatment effects, we expect mean squared treatment divided by mean squared error to be bigger than 1 only in a single direction. This is a one-directional hypothesis. And it's because this term here is always positive. That's why it ends up being a one-direction hypothesis. I should note that that doesn't mean that this ratio can't be 1. So these are expected values, these are averages. Think about like the expected value of the probability of getting 2 heads in a row. The expected value, if you had to round, would be less than 50%. So it's unlikely to happen, right? The expected value is lower than a flip of a coin, but that doesn't mean it's impossible to happen. So if I had to make a prediction, are you going to get 2 heads in a row? Well, I'd bet my money on no, because there's a 75% chance I'd be right. However, there's variation around that. Sometimes I'm right, sometimes I'm wrong. So here, the average, on average, I'd expect this to be a number of 1 or bigger than 1, but sometimes it's not, and that's okay. That's just random variation. I will say, maybe I should point out that how you do know you have an error if you're doing this calculation is if it's negative. This number will never be negative. The F statistic will never be negative. All right, so ANOVA calculations are typically done on the computer. We don't do this stuff by hand. In the textbook, there's a couple of different softwares, Design Expert, JMP, and Minitab. Honestly, I've used Minitab. I haven't used the other two. I haven't used Minitab extensively by any means, but that's what's done in the textbook, and you can look in there more. It discusses some of the different summary statistics that you can look at, and actually this is a good thing. So one thing to realize in this course and with any stats course or really any course is that when you're actually doing this and work, different companies use different types of software. So it's really good for you to get used to seeing output from different kinds of software. So these are 3 kind of different ones than what I would have recommended. If I had to pick 3 softwares to do design of experiments in, it wouldn't be these. But it's really good for you to see these, and it's really good for you to get used to seeing output from these. So actually for this reason, though we'll do demonstrations in R, we'll actually look at the output from the other software in the notes, and of course the textbook has that too. So we'll be, honestly, I'm just going to screenshot stuff from the textbook for our notes to look at this so that we can actually get used to interpreting the different pieces from the different software, because the goal is to find the information from the theory in the software output. It's not to be super dependent on, well, I only know where things are in JMP output, or I only know where things are in Design Expert output. No, you should know exactly the statistics you're looking for, and you should be able to look at output from any program, even if you've never used it before, and be able to identify which are the components that you need. So in the next video, we'll jump into a few examples which use some of these different softwares and talk about the example, how we set it up, and then how we interpret the results.